and we'll go get the shop. Take it off. Okay. Oh. Only this section of the makes it like heat. Two, wait. Go right now. We could wait. Well, we should have been with that. It's why is this on like humans? Do you see? Okay. Let me. Oh. Pero, last time I took it on science chemistry. Last two exams, same. Because this guy will fix it tonight. You can't read through.
Yeah, because I have a core. Oh, yeah, I should, I used to, but it's a C. Yeah, I have a C. That's what I need, because I forgot the ball thing. But I guess I'm gonna. Box of kids. Yeah. I have boxes of this. It's gonna be nice flat. Actually, don't like. Why? It like, it like bumps into things all the time, which is my other one doesn't. My other one's like bigger. The one's like this, and of course it's not this way. I'm thinking like you could put it on the wall, nice flat. I think that's what it's for. Like for behind stuff, right? How much does it cost? Like $30? I see a 30. Yeah. That's true. I know it was this morning I was like, my goodness. So I'm gonna start it to look. I think there was a little too long. So it's like I'm gonna get this. That's all. I didn't see them. I'm not really. I just put it off to because if I don't, I'm not gonna change it either. Did I put for me? Yeah, because if I'm writing, I'm gonna sleep. I don't want to sit there. I don't. So someone takes this. Yeah.
Yeah, I mean.
I think I'm like, oh, this one. So I think. See the problem? Maybe. One of the first things. We'll figure that out until the fall. Yeah. It's fun. I think. Do you know what all comes up? Yeah, they sent out the sheet. With what your section, yeah. Didn't they use a 4-year rule? No good for no. Yeah, they did. So you know which sections to choose, and I chose the one that has the Disneyland. So like everything like it's an album? Yeah. It said on the sheet, I'm pretty sure. Nice. I'll do that. I think I'm just gonna be all done. So I'll keep. Oh.
Right, it's 3 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so today's day 2. So today we'll be going over fluid statics, and so we're basically going to be looking at fluid that is well, static, not in motion. And so what that basically means that we'll be looking at objects submerged in water or any other fluid and kind of see what that looks like. Okay. All right. So some announcements. We just saw each other yesterday, so not too much to update you guys on. But just a reminder that homework 1 is due this Friday. So there's quite a few problems on it, but I would definitely get started on it, especially after today. So after today, you should be able to get a good start on that homework, and then you'll be able to finish it up based on the information we're going to cover tomorrow. Okay. The other thing that's due this Friday is your introduction email. So I know I've already received quite a few from the class. So if you haven't had a chance to send me an email, please make sure to do so before Friday, just so I can give you credit for that as well. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go and get started. All right, so subject for today is fluid statics. All right. So, like I just mentioned just a couple minutes ago, fluid statics is the study of fluids that are not in motion. And in all honesty, fluids that are static, not in motion, are really not super interesting. So we're not actually going to be talking about the fluids themselves all too much today. But what tends to happen is that when you have a fluid that is static, stuff still happens within the fluid. The main thing that happens is that pressures will start to develop within the fluid itself. So this idea of hydrostatic pressure is what we're going to be focusing on today and tomorrow. Okay. And so what that basically means is that if you were an object, or even just, if you're just a particle that's submerged in a fluid, you're going to feel a pressure. You're going to feel forces that the fluid is just exerting on you passively. All right, so what that means basically is that if you have a pool of water, or any fluid, but generally if you're going to be submerged in something, you probably want it to be water. Okay? You don't want to be submerged in a pool of honey. That might be a little bit hard to get out of. let's say that you're a person that is kind of at the bottom here. So let's say that you are in a swimming pool or something, you kind of swim your way to the bottom, or maybe you're diving or something like that. Okay. What's going to happen is that the fluid, just by the sake of it being a fluid, is going to exert pressure forces on you or any object that is submerged in water. And that's something that you actually feel, right? So, I think this is probably something that I think most people kind of understand. And so if you ever watch any kind of National Geographic kind of documentary of deep sea diving or submarines that go deep under the ocean, you kind of hopefully are familiar with the idea that, any structure or any kind of device that is designed to go deep under the ocean has to be able to sustain these very large pressure forces. So that's essentially what we're going to be talking about today. So I would say, for most modest, for relatively modest heights, even from a swimming pool, this is not something that you feel all that much, but it does become very relevant in when height differences are very large. So what we can say is that the pressure develops in a fluid mostly due to height differences and gravity. I should say depth. Maybe depth is the easier. We'll kind of go through the derivation of that kind of relationship later. So the first kind of, I would say, kind of real formula that we're going to go over in this class, and thankfully it's a relatively simple one. So we start pretty easy, before we get to kind of more complicated stuff. Okay. And the main reason that this occurs is the fact that the deeper and deeper that you go within a fluid, basically everything on the bottom layers of the fluid has to support the weight of the fluid on top of it. Okay. Because remember, everything here is static, right? So static means that it's not moving. So if you've taken a statics course before, I think most people we have at this point, you'll know that when you have a static situation, the sum of all the forces have to be equal to 0. Okay. So if you take a block, you just take a block of random fluid here, and we'll go through the formal derivation a bit later. But basically, this block of fluid, has a particular weight, right? We basically have the volume of the box multiplied by its density, right? And if you basically compute all the forces, right? The force that's on the bottom of this box here has to be larger than all the other forces because it also has to support the weight of the fluid above it. Okay. And that's essentially the main reason why pressure forces develop is that these pressure forces develop just as a way to support weight. Okay. Okay. And one more thing before we kind of jump into everything. Let's kind of remind ourselves for the dimensions for pressure. Okay. So pressure, remember, is described as a force divided by area. Okay. And if you want to put this in our typical kind of mass, length, time, dimensions that we talked about last time, right? Force was kind of that weird one, which was, a mass times in length divided by time squared. Okay. Area is length squared. Okay. And so, we cancel these out. We get that the dimensions for pressure is mass over length times time squared. Okay. But I think for our purposes, it's a little bit more useful to think about pressure as a force over an area. Okay. Or in other words, we can say that pressure is a force that's distributed over an area. Okay. So we're going to use that fact, and so we're going to do some pretty interesting kind of statics problems. Maybe not today, but on tomorrow for sure. Okay. That's one thing to kind of remember as we're kind of going through it. So my plan for the next 2 days is that today we're going to be kind of just introducing these concepts. We'll do a couple of derivations. We'll introduce the formulas. We'll do some more simple examples today. We'll go over the concept of manometry, which is what you're going to use for the medical device problem on your homework. And then tomorrow, we'll get into more, I would say, a bit more complex examples that'll help you with the homework. So, okay, but that's the idea of kind of where we're going for the next couple of weeks. Any questions on this so far? Okay, good. Okay, so let's go over the first kind of main topic here, which is called Pascal's law. Okay. Right, so Pascal's law has to do with the fact of answering the question of we know that when we are submerged in a fluid, there's going to be pressure forces that get exerted onto us. Okay. So Pascal's law has to do with the fact of, what direction do these pressure forces actually act upon when we're submerged in a fluid? So I do have a derivation for this in the notes, but it's not the most interesting derivation, and I think the main point kind of gets lost in the details. And so I think what I'll do instead is I'll kind of describe this Pascal's law more qualitatively, because I think that's a bit more of a better illustration. Okay. Okay. So with that in mind, let's take a fluid. Let's take a container of fluid, and then let's submerge a relatively small particle within that fluid. We have our container here. We have our fluid. Okay. We have a kind of small little particle here. Okay. Now the reason I choose a particle is things do get a bit more complicated once our objects have relatively complex shapes and different surfaces. We'll cover that tomorrow. But today we're just kind of worried about just a particle that's submerged. Okay. All right. And if you've kind of already read ahead to buoyancy, we can assume that this particle has relatively the same density as water. So it is suspended. It's low. Okay, so it doesn't fall all the way to the bottom. It doesn't float on top of the surface. It's kind of suspended somewhere in them. Okay. Okay. All right, so what do we expect, right? So if you're an object that's kind of floating in the water and there's no motion in the water at all, so there's no currents, there's no direction, what do you expect to happen to the particle, right? We expect the particle to just stay there, right? Because there's no motion in the fluid. Okay. Right. So of course not accounting for buoyancy forces or anything like that. If you have an object that's submerged in fluid, the fluid is completely static, right? There's no reason or there's no way for that particle to ever move in any particular direction. Okay. But what we just finished describing was that by nature of this particle being submerged in fluid, there are pressure forces acting upon it. Okay? So we have hydrostatic forces acting on it, right? So how can we reconcile that, right? So how can we have an object which we know has forces being applied to it, but it's still being stationary, right? The only way that can happen is that all the forces sum up to zero. Right? So that's kind of the master equation for statics, right? So you take all the forces that sum up on an object and they should equal to zero. Okay. So then what does that mean for our pressure forces? So then our pressure forces, right? We know that there are pressure forces acting on this object, right? And if we assume that the object is relatively small, we can assume that the pressures are uniform all throughout. Okay. So what that means basically is that all the pressure forces, right? What that basically tells us is that all the pressure forces are acting equally around the object, right? So there's no kind of preferred direction, and there's no preferred magnitude, okay? Such that all of the pressure forces on an object cancel out. Right, and so with that, we kind of arrive at kind of the main, I guess, statement of Pascal's law. All right, so Pascal's law states that the pressure at a point in a fluid at rest is independent of direction okay? So all that means that the pressure forces don't choose a particular direction. It's going to act equally in all directions. Okay? As long as shearing forces are not present, which basically just means that the fluid is going to be stationary. All right, so what I've boxed there is just the statement of Pascal's law. All right. Another way to kind of state this is that pressure itself is not a vector quantity, right? So it's not like a force or a velocity, where force and velocity are vectors, and so vectors have both magnitude and direction. Pressure doesn't really have a direction. Pressure is just the magnitude of force per area at a particular path. Now, the forces that result from the pressures, those are vectors, right? And those do have a direction, and that direction is quite important. But we'll cross that bridge when we get there. But pressure itself is just a scalar quantity, right? So there's no sense of direction with pressure. Okay. Okay. Any questions on Pascal's law? Okay, good. So Pascal's law was one of the first, I would say, kind of formalized theories for hydrostatics. That's why we named the unit for pressure after him, because he was the one that kind of formalized his theory. Okay, okay, good. All right, so next thing we're going to go over is we're going to talk about how pressure actually varies within a fluid. Okay. So we've just established that at any particular point, pressure doesn't have a direction, right? But if you compare the pressures at two different points, we do expect the pressure at those points to be different. Right? So we draw our pool of fluid again. We have P1 here, 0.1. We have 0.2. Okay. I just drew those arbitrarily, so it doesn't really exactly matter where those points are located, right? But the fact that we have two different locations here, we do expect the pressures to be different at 0.1 relative to 0.2. The question is, how different are they, or how exactly do they vary? And can we come up with an equation that tells us explicitly how much they actually vary from each other? Okay. Okay, so that's what we're hoping to solve this. Okay. All right. So to actually come up with this relationship, we're going to go back to the beginning of the lecture today, and let's draw a box. Right, so let's draw a box within the fluid itself. Okay. So this is just an imaginary box. It's not like I took an Amazon box and just submerged it in water, although I guess you could do that as well. But this box, just for our intensive purposes, is imaginary. Okay. Okay, so the dimensions of this box, we're going to draw, well, first let's draw our X, Y, Z axes, right? So let's assume the Y direction is going up, X direction is going horizontally across, and Z direction is going out of the page, okay? Right, so the dimensions of this box, the horizontal dimension of the box, we're going to call delta X. The height of the box, we're going to call delta Y. And the depth of the box, we're going to call delta Z. Okay. One thing we're going to identify here is we're going to be drawing, we're going to identify the centroid of the box. Okay. Right, so that point that I just drew in the middle of the box there, that is the centroid. And what we're going to assume is that we're going to assume that we know the pressure at the centroid of the box. That's going to assume to be P. Right, so the pressure that we're essentially going to be doing a free body diagram of this box, and we're going to compute the pressures of each of the other faces. But P, the pressure at the centroid, is going to be our reference. Okay, because the question that we're trying to solve here is that if we were to travel in the x direction, y direction, or z direction, is the pressure going to vary in this fluid? Right, so we're going to use this very simple box here and to kind of answer that question. All right, any questions on just kind of the setup for this before we kind of really jump into the math? Okay. Okay, good. Okay, so we're gonna tackle each direction kind of individually just to kind of make things a bit simple. Okay. All right. So first, actually, let me kind of draw kind of the back side of the box. Actually, let me redraw the box down here just because the figure up here is getting a little bit. Okay, so we have our box here. Right, and then what I'm going to do is I'm also going to kind of draw the back side of the box, just kind of clarity's sake. Okay, good. All right, and so in order to basically do our free body diagram, and in order for us to compute our forces, we need to know basically come up with an expression in terms of how the pressure varies to each face of the box. Let me switch off the red because that's a little bit obnoxious, just be completely writing in red. Okay. Okay, because what we know, right? So just kind of just based on Pascal's law, right? We know that there's going to be a hydrostatic pressure force that's being applied on each of the 6 faces of this box, right? So we're going to have a force applied on this face, a force applied on this face, this face in the back, this face in the front, and from the bottom. Okay. And in fact, let's go ahead and label all these forces. We'll call this F1, F2, F3, F4, F5, F6. I know with my drawing, it's a little bit hard to see, but basically the way I drew these is that F1 and F2 are going in the Y direction. F3 and F4 are acting in the X direction. And then F5 and F6, those are in the Z direction. Okay, so we need an expression basically to relate F1, F2, F3, F4, F5, F6 to the pressure at the centroid of the box, because that's kind of what we assume. Okay. Okay. So let's do F1 first. Okay, so let's do F1. We're going to say that F1 is going to be basically the pressure that's at the centroid of the box plus a variation term multiplied by the area of that face. Okay. Okay, so what does that look like? So basically, this is going to be the pressure, P. So for P here, this is the pressure at the centroid of the box. Okay, plus, right? Since F1 here is acting on the top face of the box, right, we're going to travel in the y direction in order to get there, right? And so that's going to cause a variation in pressure. Okay, so that variation in pressure is going to be equal to partial P, partial Y. Okay, so we have the derivative of the pressure with respect to the y direction. Okay. Right. So I'm using partial derivatives here because we're assuming that pressure could also vary in x and z direction as well. Okay. And then we're going to multiply that. We're going to multiply that by the distance that we're going to travel from the centroid of the box to the top face of the box itself. Okay? And so that distance is delta y over 2. So this delta y over 2, this is the distance from the centroid to top surface. Okay. All right, remember it's delta y over 2 because remember we defined delta y as the total edge length in that y direction. So if we're going from the centroid to the top, that means we're only traveling half that distance. Okay. And the other thing is we're going to multiply this by the area of the box, area of that side. Excuse me. Remember, to go from a pressure to a force, we have to multiply the pressure by an area. Okay. And the area of that face, area of that face is delta x times delta z. Right, so delta x, delta z, that product is the area of that top face. Okay, because remember to get to a force from pressure, you take pressure, you multiply by area. Pressure is just force divided by area. Okay. All right. Good. Now we can use this exact same logic to come up with F2. Okay. So F2 is going to have a very similar expression, but you can see that F2 here doesn't act on the top surface of the box, it acts on the bottom surface of the box. Okay? So instead of traveling up by delta y over 2, we're traveling down by delta y over 2. Okay? So F2 here is going to be P minus partial P partial Y times delta y over 2 multiplied by delta x delta z. Right, so the bottom surface of the box has the same area, so it's still delta x delta z, but we subtract the variation instead of add it, okay, because we're traveling in the negative y direction. Okay, so now we have everything we need to basically perform a summation of forces in that y direction, okay? Now we're ignoring F3, F4, F5, F6 because those are forces in the X and Z directions. We'll come back to those in a second, but for now we're just going to focus on the Y. So let's sum up all the forces in the y direction and then set it equal to 0. Okay. So we have summation of forces in the y direction. All right, so if we go back to our diagram here, we can see that we have basically two forces in the y direction. We have F1 that's pointing down and F2 that's pointing up. Okay? So we have F2 minus F1, right? And we'll plug in for F2, F1 in a second, but let's write up the expression first. Okay. Now in the y direction, we have one additional complication here. So in the y direction, like we mentioned at the beginning of class today, we also have to account for the weight of the box itself, right? Because the box itself is containing a certain amount of fluid, right? So that fluid has mass and that fluid has weight as well. So the weight of the fluid is in a minus y direction. Okay. It's going to be minus rho, the density of the fluid, multiplied by gravity. Right, so if you want to use shorthand, rho times gravity, remember a specific weight, so you can plug in gamma for this, but I'll keep it in terms of basic variables for now. Okay. Right. And so if we multiply rho times gravity, that's going to give us a force or weight per unit volume. And so in order to convert this to a force, we have to multiply it by a volume, which is going to be the volume of our cube, of our box. Okay. So we're going to multiply this by the product delta x, delta y, delta z. So this right here, this is the weight of the fluid contained within the box. Right, so all this is equal to all this is equal to. Okay, so let's go ahead and plug in for F2 and F1 here, and let's see what that gets us. Okay, so F2 we have just right above here. The reason my iPad is kind of glitching out, there it is. Okay, so let's plug in for F2, F1. So F2 here we have P minus partial P partial Y times delta Y divided by 2 times delta X delta Z minus F1. So F1 here is P minus P plus partial P partial Y, delta Y divided by 2, delta X, delta Z. Sorry, I made a typo on the previous term here. So the previous term here should have delta X, delta Z. So make sure you get that one in your notes. Okay. All right, and then we're going to subtract the weight of the box that we just wrote up there. So minus rho to G, delta X, delta Y, delta Z, all this equal to 0. Okay, good. All right, so let's simplify. So we have quite a few terms here that are going to cancel out. Whenever you have an equation like this where you have a lot of things cancel out, it's one of those things that's oddly satisfying. Okay. All right, so let's start with P, right? We have a positive P from the first term. We have a minus P from the second term, so those are just going to cancel out. Right, so the pressure at the center of the box is irrelevant here, which makes sense because we're coming up with a formula to describe the variation in pressure. Okay. Next thing we notice is that every single term here has a delta X, right? And since we have this entire equation equal to 0, that means we can factor out the delta X and then just divide by it. So that essentially just cancels it out. Because we divide the right-hand side by delta X, we have 0 divided by delta X, which is just 0. Okay. We can do the same thing with delta Z, right? So every single expression here has delta Z. You can go ahead and factor that out and divide by it to cancel it out as well. And every single expression here also has delta y, right? It's just that for F1, F2, the delta y is within the parentheses itself, right? So we just kind of factor that out and combine. All right, good. So after all that cancellation, we're left with a fairly simple expression here. Okay? So what we have left is minus partial p partial y times 1/2 minus delta p partial p partial y times 1/2, okay, minus rho times g is equal to 0. Okay, so we can simplify this a bit more, right? So we can combine the two derivative terms, right? And so we get a minus partial p partial y. Okay, and I'm going to take the rho times g and I'll move it over to the right-hand side. So this is equal to rho times. Also, I don't know what happened here because my brain just colored it. That should be a y. Okay, okay. So those two derivatives are the same. All right, so we'll do one last step here to simplify. Let's just move the negative over to the right-hand side, just so we have a clean expression for the derivative. And what we get is partial p partial y is equal to minus rho times g. All right. So a little bit of work here, but I think we end up with a result that's pretty, it looks fairly simple. It's a very simple equation here, but there's a lot that we can kind of glean from it. Because basically, this equation is telling us that if we move in the depth direction, right? So we basically go either deeper into the fluid or closer to the surface. We're going to experience a variation in pressure, where that variation is dependent on two things. So it's dependent on the density of the fluid, and it's dependent on the value of gravity. Okay. All right, so a fairly simple equation, but that's essentially what it tells us. Okay. So what that tells us that if our fluid is more dense, right? So let's say that we're looking at liquid mercury or something. You're going to feel a lot more pressure going a meter deep in liquid mercury than a meter deep in water. Although if you're going a meter deep in liquid mercury, probably you have other issues because that's not something you want to be in. But also that means also that if you have a gallon of water on the moon, right? The moon has much less gravity than Earth. You're going to see less variation in pressure as well. Okay. All right. Any questions on this? How we got to this expression here? Okay. Good. All right. So I wanted to start with the y direction because the y direction is honestly the most interesting one. But let's look at the x and z directions. We'll do one of them, and then I'll convince you that the other one is exactly the same as well. Okay. All right. So let's look at the x direction. Right, but for the x direction, what do we have? X direction with F3 and F4, right? Okay. So let's come up with expressions for F3 and F4, same as what we did in the previous in the previous part. Okay, so let's go back to our figure here. F3 is acting on that kind of left side of the box, and it's acting in a positive direction. Right? So F3 here, if we come up with a similar expression, is going to be P minus partial P partial X times delta X divided by 2 multiplied by the area of that face, which is delta Y delta Z. F4 similarly is going to be P plus partial P partial X times delta X divided by 2 times delta Y delta Z. Okay. So exact same logic that we use to compute F1, F2, it's just that now our variation is in the X direction because we're looking at F3 and F4. Okay. Okay, so just like we did previously, let's go ahead and sum up all the forces in the X direction. Now in the X direction, we don't have to worry about any weight, just because there's no weight does not act in the X direction. Weight only acts in the Y direction. So the only forces we have in here are just going to be F3 and F4. So when we sum up the forces in the X direction, we just simply get F3 minus F4 is equal to 0. Okay. All right, so let's just go ahead and plug in our expressions for F3, F4. Okay, so that's F3. So F3 is P minus partial P partial X times delta X divided by 2 multiplied by delta Y delta Z. And F4 is P plus partial P partial X delta X divided by 2 delta Y delta Z. All this equal to 0. Okay. All right, so let's go ahead and simplify this expression. So, this should be pretty quick. So just like we saw previously, right, we can take delta X, delta Y, delta Z, and just factor them out of both terms here and divide both sides by it, right? Since we have a 0 on the right-hand side, all 3 deltas are just going to be equal to 0. They're not equal to 0, they cancel out, excuse me. Right, so that's something simple we can do. Another thing we can see is that we have a positive P on the first term, a negative P on the second term, so those two terms are also going to cancel out. Okay. Right, and so all we're left with is a minus 1/2 partial P partial X minus 1/2 partial P partial X and equal to 0. Okay. If we simplify this, we combine those two terms, we just get partial P partial X is equal to 0. All right, so that tells us that the derivative of pressure with respect to the X direction, right? So if we were to travel within the X direction, the derivative is 0, right? So derivative of 0 basically means that we're not going to experience any change at all. So if we were to travel purely in the X direction, we do not expect to experience any change in pressure. So if you were to stay at the same height, right, it doesn't matter how much you travel in that x direction, in that horizontal direction, you're not going to experience any change in pressure. Okay. We can go through the exact same exercise for z, right? And you're going to find that you get the exact same result for z. So I'm not going to go through just for the sake of time, right? But you can verify yourself, right, that we get the exact same result. That partial p partial x, so the derivative of the pressure with respect to z, I said partial z, excuse me, is equal to 0. Okay. Okay. So what that tells us is that the only direction that you can travel to experience a change of pressure is in the y direction or the depth direction. Okay. And the reason for that is because of the factor of the weight, just like we kind of mentioned at the beginning of class. Okay. All right. Any questions on this? Okay, good. All right, so last thing we'll do in this section before we do an example. I know today's kind of been a little bit heavy on derivations and theory. Let's take our derivative in the y expression again, and let's integrate it just so we can get a useful expression that we can actually use in our equations. Okay. So what we saw before was that partial p partial y is equal to minus rho times g. Right, so that was the first of the equations that we kind of derived from this section. Let's integrate this with respect to y, so that on the left-hand side we kind of cancel out the derivative, just so that we can get an expression that tells us the difference in pressure between two different points. Okay. We're going to take this expression and we're going to integrate it between two different y locations, y1 and y2. Yes. So Zoom just quizzed. Weird. Okay, we're back. Oh, can you hear me now? Okay. Yeah, sorry about that. I think Zoom kind of had a little bit of a snafu. I think we're back now. Okay, there we go. All right, we're back. I apologize for that. Okay, all right, so we're going to take this expression here, this kind of simple derivative expression in y, and we're going to integrate it between two locations, y1 and y2. Okay. So the kind of situation is the following. So we have our container here, right? We have our two locations here, right? One is at a depth y1, and one is at a depth y2, right? Where y is measured kind of relative to the free surface. Okay, so y1 is at a deeper depth than y2. Okay, all right, so let's integrate our expression here. So we're going to integrate this with respect to y. We're going to integrate this from y1 to y2 with respect to 1. Okay. All right, so this is a pretty simple integral to perform here, right? So on the left-hand side, our dy and the partial y are essentially going to cancel out. Okay. And so on the left-hand side, we just have derivative of partial p, which is just simply just the difference between the pressures at those two locations. Okay, and so on the left-hand side, we get P2 minus P1, okay, where P2 is the pressure at Y2 and P1 is the pressure at Y. And then on the right-hand side, we have integral of minus rho times G dy, right? So rho is a constant, right? So we're assuming that our fluid here is incompressible. So that means our density is constant. And gravity is also a constant because gravity is just gravity. Okay. Okay. And so if we factor those two out, so we have minus rho times G. Okay. Then we just have integral from y1 to y2 of dy. Or in other words, we have just integral of 1. Right, and so what we have here is minus rho times G times y2 minus y1. All right, so that's a formula that we're going to use, and you'll be surprised. This formula actually has quite a few uses, and there's a lot of tricky, interesting ways to really use it. Okay. Okay. One other way that we can express this formula is we kind of notice that on the left-hand side here, or the right-hand side, excuse me, that this y2 and y1, this is just simply a difference in height. Which I realize, so it's kind of a small point, but I apologize. But the y2 and y1 actually isn't measured relative to the free surface, it's measured relative to the bottom. So let me just kind of redraw this figure here. When I say y1 is the distance from the bottom of the container to y1. And y2 is the distance from the bottom of the container to y2. So there was a small kind of typo on my end, so I apologize. Okay. Right. So with that in mind, then we can re-express this formula in terms of just the difference in height, right? And so if we know, right? So let's say that we don't really know the distance between y2 and y1 to the bottom, but we do know the difference between y1 and y2, right? As some height h. Okay. So we can express this formula P2 minus P1 is equal to minus rho times G times H. So that's the formula we're going to use for the rest of today. Because basically this is our way to compute pressures at different locations within a fluid. All right. Any questions on any of this so far before? Yes.
So is the y2 minus y1 is not final minus initial.
You could think of it that way. It's more kind of just the difference in height between the two.
So
So what you're gonna see is that we aren't actually traveling within the fluid. We're gonna have 2 points that are kind of predetermined, and y2 and y1, y2 minus y1 is just the difference in height.
so it wouldn't be expressed as change in y, it would just be expressed as height.
You can think of it as change in y as well. That works as well. Yeah. Yeah, I think you'll see in the next example kind of how that plays out. All right, cool. So, all right, so let's do an example. I do have one more conceptual point here, but let's do an example. I think let's do a couple examples before we go to break. Okay. All right, so let's say that we have a gasoline storage tank and we have gasoline that's sitting on top of a layer of water. So this might be a situation where maybe gasoline gets it gets out of a container and it's gotten into the ground or something. Okay, so our situation is the following. So we have our container that looks like this. All right, so we have a bottom layer of water. Then we have a layer of gasoline. And we have a free surface up here. We'll explain kind of what the free surface means in a second. Okay. What we know is that the distance from the free surface down to the interface between the gasoline and the water is 500 centimeters. And then the distance or the depth of the water layer is 100 centimeters. For this problem, we're also given the specific weights of gasoline and water, right? So the specific weight of water, which remember, specific weight is simply just the product of the density and gravity. So this is simply the product of the density of water, gravity, okay? This is equal to 9,800 Newton per meter cubed, okay? And we have the specific weight of gasoline, which is just the density of the gasoline. It's gravity. This is 7,200 newtons per meter. Okay. All right. And so what we want to do is that for this situation, we want to compute the pressure at two locations. So we want to compute the pressure at the interface between the gasoline and water. And two, we also want to compute the pressure at the very bottom level, so at the ground level of this of the situation. Okay. So relatively simple example, but this will show you how to apply the formula that we just took. Okay. All right. Any questions on just the setup for this example here? Okay, good. All right, so let's start with part one. So let's compute the pressure at the gas-water interface. All right, so this example here kind of introduces the concept of the free surface, right? So if you notice, right, when I drew this figure here, I drew this triangle at the top, right? So that triangle, whenever it's sitting on the surface of the water, we call this the free surface. Or in other words, this is going to be a surface that's exposed to atmospheric air. Okay. So that's always very useful to know. And in fact, whenever you're doing a hydrostatic problem, right? You should always try to identify the free surface because that's going to act as your reference point. Okay. Now, technically, the free surface is at atmospheric pressure, and atmospheric pressure is not zero. We'll talk about that in a second. Okay. But, just for our intents and purposes, for calculations purposes, we can assume gauge pressure. Under gauge pressure, we assume that atmospheric pressure is zero. Okay, so we're going to use the free surface as a reference. And we're going to assume that the pressure is zero at that free surface. Okay. So what you're going to see is that this is just a reference. You could very easily plug in the value of atmospheric pressure there. Your answer is not going to change all too much. It's just going to be offset by that atmospheric pressure. Okay. Okay, but that does help us out because that does allow us to apply our formula, right? Because our formula here, you can see we can only compute the difference in pressure between 2 points, right? And so in order to compute the absolute pressure, we do need a reference. Okay, so using the free surface as a reference, let's do part one. Okay, so for part one, we're basically going from the free surface down to the gasoline water interface. Okay. Now from the figure, we can see that the height difference or the difference in elevation between those two locations is 500 centimeters. Okay. So let's apply our formula. We have P2 minus P1 is equal to minus rho times G times H. And let's plug in the values of what we have. Okay. All right. So in this situation here, our free surface is the upper surface. So this will be location 2. And the gasoline water interface is location 1. Okay. And so based on our assumption, we know that P2 is equal to 0, right? Because that's where our free surface is. So let's go ahead and plug that in. Right, so P2 being the pressure at the free surface is equal to 0 minus P1. Right, so P1 is what we don't know, so P1 we'll leave as a variable for now, right? So we're going to solve for it in a second. Next thing we have here is the product of the density of the fluid and gravity. Okay. Now for this, you have to be a bit careful because you have to think about kind of which fluids that you're passing through in order to get between these two locations. Okay. So as we travel from the free surface down to the gasoline water interface, we're only traveling through the gasoline. And so that means that this product of rho times G is going to be just the specific gravity or specific weight, excuse me, of the gasoline. We'll bring in the specific weight of the water in a second. Okay, and then after that, we just multiply that by the height, which we know. We know that the height here is 500 centimeters, or if we're putting it in standard meters, this is 5 meters. All right, and so from here is just a simple multiplication, right? And so first thing we should see is that our two negatives are just going to cancel out. And so we get is P1 is equal to the product of the specific weight of the gasoline, which we know is 7,200, multiplied by the height, which is 5 meters. And so we multiply those two together, we get 36,000 Pascal. So the pressure at that location between the gas and water is 36,000 Pascal. All right, any questions on how we got that result there? Okay, good. All right, let's do part 2. So part 2 of the problem, we're going all the way to the bottom of the tank here. We're going to the bottom of the water layer, which is that location there. Okay. So we're going to apply the same formula, right? So you can do this one or two ways. So you can go from the very top of the surface down to the very bottom, or we can just go from the interface between the gas and water, just because we just computed that pressure, down to the bottom. Okay, so let's do that, but I'll show you the other way as well. So let's set it up where our gas-water interface is location 2, and the bottom of the tank is location. Okay. Now this is pretty simple because in this case, we're just traveling through the water. So we're going to set up our same formula. P2 minus P1 is equal to minus rho GH. So in this situation, location 2 is the gas-water interface. And so we know what that pressure is. That pressure we just computed was 36,000.
I think you're off by like 0.
Let me see. Five. 500 centimeters.
It's divided by 2. So it should be 3,600.
500 centimeters is 5 meters.
Oh, it says 0.5 in the notes.
Yeah, I noticed that too. That's a typo. I think what I meant to say was this was only 50 meters and this was only 10 centimeters, but we're going with 500 and 100. So yeah, yeah, I noticed that too. Okay. Yeah, so the pressure at the gas-water interface is 36,000 Pascal. So this is a really deep gasoline layer. So 5 meters is huge. And then P1 is what we're solving, but we don't know what that is. And so rho times G here, this is just going to be for the water because we're only traveling through water between these two locations. Then H here is 100 centimeters, where 100 centimeters is just 1 meter. So yeah, in the notes there is a typo just because I think maybe I meant to 500 millimeters, but yeah, well, we're going with the values that I have here. So 100 centimeters is 1 meter. Okay. Okay. All right, and so we basically, if we solve this equation for P1, okay, we get P1 is equal to P2 plus specific weight of water times 1 meter. Right, so this is equal to 36,000 plus specific weight of water, which is 9,800. And so that gives us 45,800 Pascal. Okay, good. So that's one way to do this this part, right? And so if you know one of the intermediate pressures, you can just use that to go from there. Okay. Another way you can do this problem is you can go straight from the free surface down to the very bottom. But you have to keep in mind that in this situation, you are traveling through two different fluids. Right, so this is part 2 again, but traveling from the free surface. Okay. All right, so same thing, right? So we have P2 minus P1, okay? So this is advantageous just because we know that at the free surface, our pressure there is 0, or that's kind of what we assume, okay? But on the right-hand side, we're going to have two different terms here to account for the fact that part of this we're going to be going through gasoline, and part of this we're going to go through water. Okay. And so basically the way that works is that you're going to add a term here for every single basically layer of fluid. You're going to multiply the specific weight of that fluid multiplied by the height that you're traveling through. Okay. So in this case, you know, we have the specific weight of gasoline multiplied by the height of our gasoline layer minus our specific weight of water multiplied by the height of our water. Okay. So we get minus P1 is equal to specific weight of gasoline, that is 7,200 newtons per meter cubed. Okay. Hg here, the height of the gasoline layer is 5 meters, minus specific weight of water, 9,800 newtons per meter cubed, times the height of water, which is 1. Right, and so you do the arithmetic here, you cancel out the negatives, you should get the exact same solution. You get P1 is equal to 45,800. All right, any questions on this example here? Okay, all right, so let's take a break. I'm getting a bit tired. So let's come back at 4:30 and then we'll continue the rest of it. Yeah. Yeah.
It's kind of on the top and show the bottom.
Yes.
So P2 is always something above the P1.
Yeah, I would use it like that. I think once you kind of get good at this program, you can kind of play around with it and don't notice it, but I would take location 2 to always be.
Yeah, okay.
Yeah.
They've already done it. Is there a solution?
There is a solution. They said they're gonna stop it from exploding. Like the partners or something like that.
He's like, they told me there were 2 options. Either it leaks or it explodes. And I didn't take either option or something like that. It was a super speech that he did. He's like, there's a piece. Nothing lost it.
So cool.
My friend's family had to evacuate. They were living in a trailer park at those there.
Right.
Oh, they're back home. They got back home yesterday. But
Is it
they had
safe?
to- That was fine. It's safe now. Like they contained it.
Is it cracked?
No, like they stopped it completely. Look it up. That's what I was
What?
talking about the speech.
Oh, okay, so that he was like saying, no.
They gave me two options and I said no. Oh, but that engineer on record to do it, bro. He's done for. Now that you have the information, or yeah, there's a whole video. He got like a scale.
I can't use the one. That was the register.
And your sunglasses go from.
Oh, yeah, it cracked and then it just, leaked. Okay, it's fine, it's already done.
Wait, it's like I saved him. What did the company do today?
Where?
Company D. The discount like,
Oh, sure.
and because my friend got a flyer. He was talking about cast member and we used to hear it. We had to go. Dude, she spent $50.
Did she take her stuff?
She put a lot of stuff. I was spent 80 something. But
Oh,
I can still hold on to it.
yeah. Oh, it's not yet. It's so funny.
Cheesecake Factory.
Oh, I have to know. What do you think about it? Which one?
My sisters.
Both of us. I wanted the Jess. So I got the matching blanket. I got 2 pillows, blanket, and then this is the jacket. It's cute.
Yeah.
For my mom and my sister. I had one. Didn't have a medium, so I made friends with this lady who lives in Epcot. Over there. The ears were $5.
The lady who was from Epcot, but she was here.
Like she's here visiting here. So then she's like, contact me if we get stuff. And I bought a bunch of pins. Yeah. And then that crew neck, it cost me $25, but it's normally 130. It's Stony Clover.
It's good. It's like Epcot.
And it's really high quality because it's
Like 150.
I spent only 84.
That's really good.
My friend, she got a lot. She got these earrings from Girls Crew. This one. We got these to take our grad photos next year. Because they were $1.
That's all.
Yeah. And I'm gonna rhinestone them.
Oh, she's doing something. Oh no. Interesting. I didn't start cooking this.
But yeah, she did a lot of stuff. She's the one who spent 100. She got me a baby together.
Did you already apply for
Mm-hmm.
see? Do they send you like what you and the gallons or whatever?
No. I just applied for graduation and I paid for the fee and that's it. Because that's what I found out. You know how I couldn't enroll in those classes because like it said I wasn't graduate standing? It's because I didn't apply. Once you do that.
That's it.
Yeah. I was like, with his friend. Because he's like my neighbor. He lives like at the end of my cul-de-sac. The house behind that is his house. So like from his parents' window and my I can see each other's windows. You can see, yeah. That's where we grew up together. So we could see each other from like our parents' windows. Well, my window and his parents' windows. It was like, oh. He now I felt like if he lives far away. Like I haven't seen him forever. Because I'm like a couple weeks there. He's like, it's called cheesecake. Because normally it's a blanket for us. It's like, really.
Like these? No. No, those are much. These stars.
Oh, these are dry clean. Good girl.
It looks like
In the morning, if there's traffic, it'll take me 45 minutes. If there's no traffic, it'll be like 25. I live relatively close. Because I live in the Corona right that borders Yorba Linda.
Yeah.
I don't have my foot. Why don't you put them?
Oh, but it's all just free.
Mm-hmm. Yeah, I live like right here. You see, there's this is the airport. My house is like right here. So I'm right on the freeway right here at the auto center where the internet is. So then I skipped all the traffic from the Riverside coming up to the. So
And
people who
there's-
live in
So the
Riverside.
traffic's here.
Uh-huh.
Okay.
I only get like 10 minutes of traffic and then the rest is free flowing.
I think it's safe for my house, like the first like 2 miles, it's like for some reason.
Cause I have a lot of friends that live in Riverside. And then it'll take them like an hour and a half to 2 hours to get. I'm like, yeah, we don't take fast track. I'm like, you're killing yourself, bro. I would just.
I get mad when I have 2 classes and I have to like drive back and forth.
All right, it's 4:30. Let's get back to it. Okay. All right, so we just finished this example, kind of our first example with hydrostatics. So I have more examples today. That's kind of just planned for the rest of the day. But you know, I did want to kind of make one conceptual point before we move on. Okay. All right, so what we've seen so far is that you know the variation in pressure or the difference in pressure in a fluid really only depends on the height difference. And so the question now becomes, you know, does it matter kind of the shape of our container of our fluid? Because everything that we've looked at so far has been kind of fluid contained in a container, right? And so if you had a container that was kind of very thin, this versus a container that's very wide, or maybe a container that has kind of an interesting shape. And so let's say that we draw the free surface on each of these. Because what we know, or kind of what we've experienced, is that you know the variation in pressure comes directly as a result of the weight of the fluid, right? And so you would think maybe that you know if you had a wider container, right, you get a stronger variation in pressure, right? Because there's just more fluid in a wider container, right? Well, it turns out that you know the pressure calculation actually already accounts for this. Because remember, pressure is not a force, right? So pressure is not directly a weight, but it's a weight distributed over an area. So just whatever the cross-sectional area is, whatever kind of the width is, you know, it kind of gets canceled out. So in all of these cases here, and just pretend that I kind of drew these well, that the pressure variation from the top to the bottom of the container will be the same. So the only factor that matters when you're computing pressure variation is just height. So the shape of the container does not play a role at all. Okay, and that makes sense too, right? Because I think probably the location or the place where you see this the most is in the ocean, right? So there's no body of water that's deeper than the ocean, right? And the ocean doesn't exactly have a shape unless you count planet Earth as a shape. And so it doesn't matter if you're in the Pacific Ocean, Atlantic Ocean, if you go 3 miles deep, you're going to be feeling the same pressure. Okay. Okay. But we can actually play around with that and actually use that to our advantage a bit. So let's do our next example here. So this example kind of is it's not really a calculation example. This one more is kind of just a conceptual example. But this shows you how a hydraulic jack works. Okay. Okay, so hydraulic, basically, if you're not familiar, hydraulics are types of engineering devices that use liquid and most time, you know, water to kind of power their system. Okay. Okay, so what I'm going to draw here is just kind of a very simplified kind of drawing of a hydraulic jack. It doesn't look this simple in practice, but I think this kind of works for our, for our purposes here. Okay, let's kind of draw two columns here. So one of them is going to be very thin, the other is going to be very wide. Okay, and on both columns here, I'm going to draw a block. Right, so the small block we're going to say has a cross-sectional area A1, and the large block here has a cross-sectional area A2. Okay, and you can see that they're connected, right? So there is a fluid that connects both of them together. And so the idea with the hydraulic jack is to use this idea of hydrostatics and pressure to generate mechanical advantage. Right, so just as a refresher, mechanical advantage is the idea of applying a certain amount of force in one location, but then having just the mechanics, the kinematics of the mechanism amplify that force at another location so that it helps you kind of perform tasks that you wouldn't be able to do yourself. Okay, so a pulley, I think, is the first piece of mechanical advantage that you learn about, but you can use hydraulics in a very similar way. Okay? Okay, so what we want to do is we want to compute. Let's compute an expression for the mechanical advantage applied on the second surface A2. So basically, we want to compute an expression of the ratio of the output force on A2 divided by the input force applied on A1. Okay. So the idea is that A1, that's the part that you actually operate. So you're going to apply a force here. Right, so we call this the input force. Okay. And then applying an input force on A1, that's going to push the fluid down, and it's going to push it out on A2. So we get an output force on this side. Question? Okay, good. All right. So let's use the idea of hydrostatics and let's use the idea of pressure to generate this ratio. Okay. Okay. So if you look at the diagram in terms of how it's drawn here, we can see that our two pistons, A1 and A2, are at the same height. And since they're connected by the same fluid, that means the hydrostatic pressure being applied on both A1 and A2 are exactly the same. that means P1 is equal to P2. Just because there's no height separating them, so the pressures are the same. Okay, we don't know exactly what those pressures are, just because in this case we don't have a reference surface, we don't have a free surface. But at the very least, we can say that since the fluids are at the same height, then those pressures should be exactly the same. Okay. Now, the next step here is to basically make the observation that since this jack, at least right now, is in static equilibrium. Okay. And so that means that the pressure is basically is being used to hold up both of the pistons. Okay. And that's true once we apply the forces as well. So what that means basically is that the pressure forces are going to be equal to the amount of force that's being applied divided by the cross-sectional area of that piston. So in other words, P1, right? So P1 is the hydrostatic pressure force on the input face, A1, okay, is going to be the input force divided by A1, right? Remember, pressure is nothing more than just a force divided by an area, okay? And so since we know the force in this case is the input force, we distribute it over the area, that's A1. And since the pistons are in static equilibrium, we say that P1 has to equal that because that P1 is supporting that input force. Similarly, P2, right, is equal to the output force divided by A2. All right, so now that we have expressions for P1, P2, let's go ahead and plug that in, right? Because we know that P1, P2 are the same because they're at the same height. Okay? And so we have input force divided by A1 is equal to output force divided by A2. Okay. Let's rearrange the terms here, right? So because remember, we're looking for an expression for mechanical advantage, and mechanical advantage is just output force divided by input force. Okay. So let's take A2 and let's multiply it up over there, and let's take the input force and let's divide it down over there. Okay. So we get A2 divided by A1 is equal to output force divided by input force. Right, so that tells us that the mechanical advantage that's being generated by hydraulic jack is simply just the ratio of the cross-sectional areas of the two pistons. Right, and so we were able to generate that expression there just based on our understanding of hydrostatics and just knowing that the two points in the same fluid, if they're at the same height, are at the same pressure. All right. Any questions on this example here? I know, not really a true example, and we didn't actually plug in any equations here, but hopefully that was interesting. Okay, so I do have one kind of small conceptual point here before we kind of move on to manometry, which will take us to the end of the lecture. But let's talk about the idea of standard atmosphere. All right. So if you remember from the first example we did right before the break, we looked at this, or we used this idea of free surface, where we said the free surface is one that is connected directly to atmospheric pressure. Okay. Now for that problem, we assume that atmospheric pressure is zero, but that's not exactly true, right? And so if you think about it, right now we're kind of being submersed in a hydrostatic fluid right now. It's just that the fluid isn't water, the fluid is air, right? And if you want to talk about the height of air that we're under, right, you have to go all the way up to the end of the atmosphere, right up until space. Okay. So actually right now, we are experiencing a pressure, right? So it's not that we're experiencing no pressure. We don't necessarily feel it just because our bodies are kind of accustomed to experiencing this pressure. But technically the air that's in the room right now is supporting the weight of all the air that's above here. Okay. And so what that means that there is always basically an atmospheric pressure that is present around us at any given time that does depend on height. And we kind of standardize things, and of course, this does depend on certain factors like temperature, depend on your height above sea level, things like that. But there is kind of a standard set of data that we can use just for calculation's sake. Right? And so those are called the standard atmospheric conditions. Right, and so this is assumed to be at sea level. So that's kind of the reference point because basically all the oceans in the world kind of are approximately at the same level. So that's kind of a useful reference. Okay. So when people talk about standard atmospheric conditions, we're assuming a temperature of 15 degrees C. So here's the big one, right? So the pressure of this of where we are is 101.33 kilopascal. And so you notice that's not just Pascal, that's kilopascal. So that's, if you want to do that in Pascal, that's 101,330 Pascal. Okay. Now that is a very weird and awkward number, right? So when Pascal made his law, he didn't account for the fact that air was a thing. And so, the unit of pressure that you typically see, when you're talking about atmospheric conditions is the atmosphere unit. Okay. Right. So sometimes you'll see, especially if you're talking about kind of environmental fluid mechanics, environmental science, you'll see a unit of pressure called atmosphere or ATM. Okay. So 1 ATM is equal to 101.33 kilopascal. Okay. So it's just a little bit more convenient unit of measure because 1 ATM is just standard sea level air pressure. Okay, so the density of air at standard atmospheric conditions is 1.225 kilogram per meter cubed. Okay. Okay, so these ones aren't as important, but you know, they're just useful to know. And then viscosity, dynamic viscosity of air at standard atmosphere is 1.789 times 10 to the minus 5 newtons second per meter. All right. So what that's saying is that basically sitting in this room, we are experiencing an air pressure of 101.33 kilopascal, and that's pushing on us constantly, right? So you don't feel it. It doesn't feel like you have pressure that's squeezing you. And but again, that's only just because we've kind of grown accustomed to it, just because we've lived our entire lives in that. Okay. You know, so it's not something that you actually really experience unless you were to go down to the depths of the ocean. But that pressure is always there. And if you have a proper measurement device, you can actually see. Okay. But with that said, you know, most of the time, you know, when we're doing calculations, just like we did in the previous example, we utilize what's called gauge pressure. So most of the time, you know, unless it's specifically stated otherwise, you know, most of the time you can assume that we're going to use gauge pressure. It's just a lot more convenient. So gauge pressure just basically takes whatever absolute pressure that you have and just subtract the atmospheric component. Right. So the first example that we did where we assumed the free surface was at zero pressure, in that case, we assumed that it was at zero gauge pressure. Okay, because atmospheric pressure, there is atmospheric pressure, but you know, for calculation purposes, we assume that atmospheric is zero, and that is gauge pressure. So to get gauge pressure from absolute pressure, so gauge is equal to absolute minus 101,330. It's very similar, you know, if you remember from thermodynamics, it's the difference between Kelvin and degrees Celsius, right? So Kelvin basically just is just you take degrees Celsius, you add, I think it was like 273.15 something. So gauge pressure, absolute pressure, same thing. You just subtract just a seemingly random number in order to get. Okay. So just a little bit of trivia, you know, in case you were curious about. Right. Any question on this? Okay. All right. So last topic that's going to take us to the end of class, and this will kind of give us kind of a nice setting for a lot of examples, is this idea of manometry. Okay. So manometry is very interesting. So, you know, before, you know, nowadays, you know, we don't actually use manometry for anything practical. But manometry used to be the way or the standard way to measure pressure in fluid systems. Now we don't really need this. Now we have digital pressure meters and we really don't need manometry. But as an educational tool, manometry does actually still kind of play a nice role. Okay. Okay. So manometer. So manometers were basically very simple devices that use the height of a column of fluid to determine pressure in that fluid. Okay. Right, so a very simple manometer would be something like this, right? So let's say that you have kind of a fluid that you're interested in knowing. Okay, so you have some fluid that's at some depth, okay? Then that fluid just kind of rises up until it reaches a free surface, okay? Right, and so if you could measure the difference in height between the free surface and the location that you're interested in, right? Assuming, again, that we're working under gauge pressure, so the pressure of the free surface is 0. That means the pressure that's at that point P is just simply equal to the product of the specific weight of the fluid multiplied by the height. Right? It's really that simple, right? Because remember what we said was that um, you know, um, the shape of the container plays no difference or no effect on the pressure. Right? And so if you kind of make these kind of thin columns of fluid, right, we can use those to very easily measure pressure. Okay. Okay. So that's the idea, right? Connect the fluid to are interested in computing the pressure, and then just use the height of that fluid to measure that. Okay. So this is probably the simplest version of manometer here. It just uses a single fluid. But this right here usually is not practical. Because oftentimes, if your pressures are of any significant value, right? If you have a fluid that's not that dense, and so water is a great example, then the height of your column will very quickly up if your pressures were relatively high. So in most situations, you're going to use a manometer that utilizes what's called a gauge. So the idea with a gauge fluid is one where it's a fluid with a much higher density, such that when differences in pressure occur, the height of the column does not get too high, too extreme. Okay. So this led to the development of a device called a U-tube manometer, not the YouTube that you go to watch sports highlights and stuff like that. Literally a tube that's in the shape of a U. Okay, so let's do an example to kind of show how that works. Okay. All right, so a typical YouTube manometer looks something like this. So let's say that we have a particular location here. So we'll call this location A. Okay. Right, so location A is comprised of a certain fluid. Okay. Right, so inside this bulb here is a certain fluid. So we'll call it fluid 1. This has a density, rho 1. Okay. But since rho 1 is a little bit, not too large, right? We can't really design a manometer that uses rho 1, because if you have significant pressure differences, you probably need a manometer that's the height of the Empire State Building. So we don't typically want to use that. Okay. Well, instead, we connect this to a different fluid. Okay. When we connect it to the shape of a U, a container shape of a U. So inside this part of the manometer, we have a different fluid, so we'll call this fluid 2. This will be the gauge fluid. Where the gauge fluid has a density rho 2, where usually rho 2, density 2 is much larger than rho 1. Okay, that's only just to keep the height under. Okay, and then eventually fluid 2 reaches up to a free surface, which we can denote with our triangle. Okay, so let's draw some locations on this diagram here. We'll call the free surface, we'll call this location 4. Call this location here location 3. 3 will be the same height as location 2 here. Okay. And then we'll draw location 1 within fluid 1 that's at the same height as point A. Okay. So in this example here, knowing the, I need to give you the heights too. Okay, so let's say that the height between point 4 and point 3, this is going to be H2. And the height from point 1 to point 2 is just H1. Okay, so utilizing this information, let's compute. Let's compute the pressure at location A using the U2 manometer. Right. So everything else in this problem is known. So we know the densities, we know the heights of our manometer here, right? So we should be able to backtrack from the free surface to compute the pressure at location A. All right, so let's go ahead and do that. So we're just going to do basically the same process that we did in our first example. It's just that we're going to do this in several steps. So let's start at location 4. So it's going to be kind of weird to start from 4 and then work our way back to location. Start here. So we're going to start there and then kind of work our way back. Okay. All right. So first, let's compute the pressure difference between 4 and 3. We're going from 4 to 3. So let's go ahead and set up our hydrostatic equation for this. So P4 minus P3 equal to rho 2 times G minus rho 2 times G times H2. We know that P4 is equal to 0, or means it's 0 gauge pressure, right? Because location 4 is at the free surface. Okay. And then everything on the right-hand side we know. So everything on the right-hand side, rho 2, G, and H2 are all. And so what this tells us is that P3 is equal to rho 2 times G times H2. Good. All right, so now that we have the pressure at location 3, we can then move on to the next point, which is location 2. So 3, 2, 2. Okay. So to go from location 3 to location 2, we're going to utilize the same concept that we used in the second example we did, the hydraulic pump, or hydraulic jack, excuse me. Okay. And we make use of the fact that point 2 and point 3 are at the same height, and they're within the same fluid. Right? So I know point 2 is at that interface, but technically we could say that point 2 is still within the gauge. Okay. So since these are at the same height, that means P2 must equal to P3, and we just computed P3, so P3 is rho 2 times G times H2. All right, so now let's go from point 2 to point 1. Okay. So from point 2 to point 1, we have P1 minus P2, 2, minus rho 1 times G times H1. Because now we're traveling through fluid 1, right? So we're going to use rho 1 and H. Okay, so we know rho 2. So rho 2 is rho 2 times G times H2. So let's go ahead and plug in for that. So we get is P1 is equal to rho 2 times G times H2 minus rho 1 G H. All right, and so that's basically the problem there. Because technically, we wanted the pressure at point A, but we know that point A and point 1 are at the same height, right? So 1, A, okay. And that's the height of PA has to equal to P1, and P1 we just computed right above, right? Right. So these manometry problems, in my opinion, they're not too difficult. They can be a little bit intimidating though, especially when you have multiple different layers of fluids. As long as you kind of use the same approach, you just start from the free surface. Because at the free surface, remember, you always know what the pressure at the free surface is. That's always going to be 0. So as long as you start from the free surface and just kind of take it systematically, just take it step by step, go from the free surface, just go through one fluid at a time. These problems are kind of very mechanical, right? And so you can kind of almost like sleepwalk through it. Okay, so as long as you're kind of following the steps. So I'd say that's my number one advice for manometry problems. Just start at the free surface, work your way around from there, and these problems just become almost kind of like second nature. All right, any questions on this example here? Okay, so I have one more example, and then kind of one conceptual thing for manometry. Next one is a bit more complicated, so hopefully that will kind of give you a bit more of a good practice. But a little bit of trivia, just to kind of show you that manometry was a real thing. Okay? So if you ever go to the doctor, or I guess technically you don't need to go to the doctor, you can just buy a device at CVS to do this. If you ever measured your blood pressure before, you'll notice that the units for blood pressure that's given in the hospitals is a unit called millimeters of mercury. Okay. So you'll see this a lot, mmHg. So mmHg stands for millimeters of mercury. Okay. And when you look at that, that seems like a very strange unit for pressure, right? Because pressure, as we know, pressure is a force divided by an area, which, as we know, is either Newton per meter square or Pascal. Those are the standard units for pressure. And so it's weird to see that, we use this this unit of millimeters of mercury for pressure. Because millimeter is not a pressure unit, millimeter is a length unit. So where this comes from is the fact that, in the old days, the way that blood pressure was measured was through manometry. So basically they had kind of a similar cuff. So they would have a cuff kind of set up on your arm, but they would connect that to a manometry device. Right? So where this unit comes from is the fact that, before the age of kind of digital, I guess not even digital devices, even before kind of the pumps that doctors used to have, right? The way they measured pressure was that they had a column of liquid mercury. And the way that they would measure blood pressure is by the height. Right? And they measure that height in millimeters. So when a doctor says that your blood pressure is 120 millimeters of mercury over 80 millimeters of mercury, that means that your blood pressure, if you were to connect your blood to a liquid mercury manometer, it would cause the manometer to raise up by 120 millimeters. And the reason you get two blood pressures, right? So there's your blood pressure is always given to you in pairs, and so there's a larger number and a smaller number. The larger number is what's called your systolic pressure, so that's the maximum blood pressure. So when your heart is at kind of maximum contraction, that's the maximum blood pressure. And then the second number is your diastolic pressure, which is the minimum blood pressure in your system when your heart is fully. Okay. So funny story. So a year ago, I went to see my doctor. So typically you want your blood pressure to be around 120 over 80. Okay? That's a pretty normal blood pressure. This is not connected to fluids, by the way. This is just unsolicited health advice. So I went to my doctor, and my blood pressure at the time was a 155 over 95. So I had very high blood pressure. So my doctor looked at me. He's like, "Oh, what's up? Like, why is your blood pressure so high?" He's like, "You know what? It's the." So I went to the doctor. It was about a year ago. It was kind of end of May, early June. I said, "You know what? Like the semester just ended. It was a tough semester. I'm not really happy with my job. I think I'm just stressed. You think I should see like a therapist or something?" And he's like, "No, dude. I think you're just fat." So he recommended that I lose some weight. I diet and exercise. I'm like, there's no way. I'm not that fat. But then over the summer, I lost about 20 pounds, and I checked my blood pressure again, and then now my blood pressure is healthy. So now I'm 120 over 80. So, yeah. So listen to your doctor. If your doctor says you're fat, you should probably Okay. All right. Let's get back to fluids. Okay. So let's do one more example with manometry. Hopefully this one is a bit more complicated. You can use. Okay, so let's look at a closed tank of compressed air. Okay. And let's say that air is connected to oil and a gauge fluid. We have three fluids in this case, where we want to kind of measure the pressure. Okay, so we have our compressed tank here. So it looks something like this. We have an interface here. Okay. So on top here, we have some compressed air. So that's going to be exerting kind of a pressure that's on top of the oil. Notice how it's enclosed, right? So there's no free surface on that side. Okay, so there is going to be a non-zero gauge pressure inside there. Okay. Inside the tank, we have oil. So that oil is going to be highly pressurized because of the air that's above it. And then to that, we have a U-tube manometer that is measuring the pressure. So we have a manometer that kind of comes down this. Right, and then in between here, we have another interface, right? So we change fluids again to mercury. Okay. All right, so let's go ahead and label some things here. Right, so let's say that the mercury rises up to a height here. We're going to say this is a free surface. Okay. We'll call the free surface, we'll call this location 3. We'll say that it drops down to here, which is location 2. The interface between the mercury and the oil, this is location 1. And we need some heights here. So we need this height. So the height difference between location 3 and location 2, this is going to be H3. The height difference between the top of the oil, or excuse me, from the mercury oil interface up to here, we'll say is H2. Or excuse me, let me redraw that. H2 goes all the way up to the middle of the pipe. And then H1 then goes all the way up to the air oil. Less. Okay. And then we have one more height here, which we'll call HA. Okay. All right, but let's put some numbers on this just so that we can actually compute this. Okay. So let's say that we know the specific gravities of each of these liquids here. Okay. Okay, so the specific gravity of the oil is 0.9. Okay. Specific gravity of the mercury is 13.6. Okay. Remember specific gravity, so specific gravity is something that we kind of mentioned last time as kind of a throwaway. Specific gravity is just the ratio of the density of the liquid divided by the density of water. Okay, so that kind of tells you the ratio of that. All right, so we know H1. H1 here is 90 centimeters. H2 is 10 centimeters. H3 will be 25 centimeters. And then HA will be 5. Okay. All right. So in this example, what we want to do is we want to compute So let's compute the pressure first at the interface between the oil and the air. Okay. And then let's also compute, so that would be part 1 of the problem. Part 2, let's also compute the pressure at the very top of the compressed air tank. Okay. All right, so that's our situation. So we have three fluids here, but you're going to see that we're just applying the exact same formula kind of over and over. Just like we did in the last example, we're going to go from the free surface, we're going to progress through the different points, and then we're going to end up at the locations where we want and compute the pressures there. Okay. Okay, so this one is a bit unique. I mean, first of all, we have three fluids, although you're going to see that's not that big of a complication. I think the bigger thing here is that we're working with specific gravities. Yeah, we haven't worked with those before. Okay. Any questions on just the setup for this example here? Okay. All right. So first thing, let's use the specific gravities to compute the specific weights of the oil and the mercury. Okay. All right. So we know. So specific gravity of a particular fluid, right? So we're going to use the oil first, but this formula applies for the others as well. Okay. So specific gravity is equal to basically the density of that fluid divided by the density of water. But we can also take specific gravity and utilize it to compute specific weights as well. Okay? So this is also equal to gamma of the oil divided by gamma of water. Okay. Because remember, gamma, the specific weight, is nothing more than just the product of density times gravity. So if you multiply the top and bottom by gravity, which you can do because gravity divided by gravity is just 1, right? So we're just multiplying by 1. Then we get specific weights over specific weights. Okay. Okay. And this is useful for us just because, you know, when we do hydrostatic calculations, specific weight is just a little bit more. Okay. So based on our previous example, we know the specific weight of water is 9,800 Newton per meter square, okay? Or meter cube, excuse me. Okay, so utilizing the fact that we know the specific gravity of oil is 0.9, right? That was given to us in the problem. We can basically just multiply both sides by 9,800 to get the specific weight of the oil. Therefore, we just do simple arithmetic. So the specific weight of the oil is 8,820 Newton per meter cubed. Okay. And then we can do the same thing for the mercury. Okay. Right, so for the mercury, the specific gravity is 13.6, right? And so mercury is 13.6 times more dense than water. Okay. So we multiply that out, we get the specific weight is 133,280 Newton per meter cubed. Okay, good. All right, so that gives us the specific weights of the mercury and the oil, right? Notice how we don't have the specific gravity of the air, but what you're going to see is that that's not really going to matter because we can basically assume that the air is standard atmosphere. Okay, so we're basically going to use this information here. What you're going to see is that it's even then it's not going to matter all too much. Okay. So let's do part 1 first. So let's compute the pressure at the air-oil interface. Okay. So we're going to follow the exact same kind of algorithm that we did in the previous example. So we're going to start at the free surface and then work our way around to the air-oil interface. Okay. Okay. So from the free surface, first thing we're going to do is we're going to drop down from location 3 to location 2. Okay. that gives us a height of H3, and we're passing through the mercury. So starting at the free surface. All right, so we go from location 3 to location 2. Okay. We have P3 minus P2 is equal to minus specific weight of the mercury multiplied by H3. Okay. Okay. P3 is at the free surface, so P3 is 0. Okay. We know the specific weight of the mercury. We know H3. H3 was 25 centimeters. Okay. So I got the units right for this one. So H3, 25 centimeters is 0.25 meters. Right, we take basically 133,280 multiplied by 0.25, and what we get is P2 is equal to 33,320 Pascal. Okay, good. All right, so now we know P2. Now let's go from P2 to or location 2 to location 1. Okay, location 2, location 1, they're at the same height and they're both within the mercury. Okay. Location 2 to location 1, they're at the same height. Therefore, we can say that P1 is also equal to 33,320 Pascal. Okay. Now we're going to go from location 1 all the way up to the interface. Okay. Okay. So this problem's a little bit tricky, kind of a little bit deceptively tricky, because to go from location 1 up to the interface, we're actually crossing over both H2 and H1. So the fact that this problem kind of gives you both of those heights is a little bit misleading, right? So typically, or in reality, you only really need one of them to combined, okay? But I think this is kind of a good example too, where you kind of have to, sometimes I think we get into the habit, when you're doing these problems to you kind of play the game of the problem where it's like, oh, the problem only gave me this, and so therefore I should use this equation. So this is a situation where the problem gives you a little bit extra information, but you kind of have to parse through it and say that, okay, I don't really care about H1, H2 individually, but what I do care is about the sum, because that's the total distance from location 1 all the way up into the interface. Okay, so to go from location 1 up to the interface, we have basically P interface minus P1 is equal to minus, bless you, minus specific weight of the oil multiplied by the total height, which is H1 plus H2. So H3 is not the same height. H3 is not the same height, right? So in the problem, H1 and H2 were 90 and 10 specific. Yeah. Yeah, so don't go off so don't go off, go off the numbers of that's given to you. Yeah, so the figures that are drawn to you can be a little bit misleading. Okay. All right, so let's go ahead and plug into this. And so we know P1. P1 we know is 33,320. Okay. We know the specific weight of the oil. Specific weight of the oil was 8,820, I believe. Yep. We get P at the interface equal to 33,320 minus 8,820 Newton per meter cubed multiplied by the sum of H1, H2, so that is 0.9 meters plus 0.1 meters. Okay. And so you punch all that into a calculator, and what you get is that P at the interface is equal to 24,500 Pascal. Question, yes.
These points, the point 1, 2, 3, and 4, are they gonna be assigned on the problems, or are these things that we need to assign when we get?
So, right, so for this example, I do give them to you. Sometimes I'll give them to you on the problems as well, but you should know that sometimes you have to draw them yourself. Okay. Question, yes.
So just as like conceptual, if you put a point like midway to where the air is at, would it be different pressure than the interface?
It would, yes, yeah. So if you were to put a point, let's say, maybe right here, maybe a different point right here, because those are at different heights, and so those will have different pressures as. That's actually good practice, and so if you want to find the pressure at different locations, you can try doing it at different heights and computing those ones. So I think for this problem, it's been a while since I wrote these lecture notes. I think for this problem, I kind of shortened the problem a bit, but the problem may have also asked you to compute the pressure at this kind of location here where the pipe is, right? So that's probably why they gave you H1 and H2 individually. But I think I may have shortened it so that we only compute just the interface pressure. Okay. All right, so let's do the next part of the problem. So let's compute the pressure at the top of the compressed tank right here. Okay. Okay. So if you notice in this problem, we're not given any specific gravity for the air. Okay. So that's pretty standard, right? So air and water are kind of the two fluids that I think people just generally expect you to know the properties of, right? And so if it's not given to you, you can assume that the air is standard at. Okay. Okay, so let's do part 2. So let's assume just for this example that air is at standard atmosphere. And if you go back to our our little kind of border there on standard atmosphere, right, you'll see that the density of air at standard atmosphere is 1.225 kilogram per meter cubed. Okay, so then we can use this information in our manometry calculation. Okay, so the air at the top of the tank, or the pressure at the top of the tank, if we just go straight from the interface, okay, so we take P tank minus P interface is equal to minus density of the air multiplied by gravity multiplied by H air. And remember, don't get confused between density and specific weight, right? So if you have density, remember you have to multiply by gravity in this equation, right? If you're given specific weight, then you don't have to multiply by gravity because gravity is already kind of factored. Okay, so P tank is equal to P at the interface minus rho air times gravity times H air, okay? All right, so we know P at the interface. So P at the interface is what we need to solve for. So P at the interface is 24,500 Pascal. Okay. All right, and then for everything else, we can just kind of plug in, right? So the density of the air is 1.225 kilogram per meter cubed. Okay. The acceleration due to gravity is 9.8. meter per second squared. Then HA, the height of that section there is 5 centimeters, and so that's 0.05. Okay. Okay, so if you multiply all that out, so let me just pull up my calculator real quick. This is just something I added just now. Okay, so take 1.225, multiply by 9.8, multiply by 0.05. We get a pressure difference of only 0.6 Pascal. Okay. And if you subtract that, okay, so we have 24,500 minus 0.6. You can see that barely makes a difference, right? So 24,000, we have 24,499.4 Pascal. All right, so basically we can assume, if you have a compressed air tank, that the pressure at the bottom of the tank is basically the same as the pressure at the top, okay? And remember, the reason for that is just air is just so much less dense than any kind of liquid, right? So because the density of air is so low, right, any kind of variation in air pressure, is usually pretty negligible. So that's kind of an important point to kind of remember, kind of a practical point, right? So, just kind of remind yourself that, whenever you have a tank of compressed air, even if it's, 3, 4, 5 meters tall, usually it's not going to have that much difference in pressure just because the air just has such low density. Okay. But that's also a very interesting point because, if you look back at our kind of our section for standard atmosphere, right? Standard atmosphere, we're sitting underneath basically so much air that the air pressure that's on us right now is 101.33 kilopascal. So that just tells you just the vast volume of air that's on top of us and just the vast amount of distance it takes to get from the surface of the Earth up to space, right? So space technically is the true free surface because there's zero pressure in space, there's zero oxygen in space. And so just the fact that, standard atmosphere has such a high, absolute pressure means that there's just a huge, huge column of air on top of us that's causing it. All right. Any questions on that? Yes.
So if the air was replaced with water, it would be a lot different though?
Exactly. Yeah. So water has a much higher density than air. And so, even though that distance is only 5 centimeters, you will see a difference in pressure if that was water.
So it depends on the density of the liquid.
It does, yes. Okay. All right. So I'll make one final point today, and then we might get started on the next one because the next topic actually is pretty big. But the last topic on manometry is this idea of an inclined tube manometer. So I don't have an example for this, which is kind of surprising to me. But inclined tube manometry is kind of more of a curiosity. It's kind of more of an academic thing more than anything that's practical. Okay. Okay. Right. So inclined tube manometry was kind of a big thing for a while, kind of before the age of kind of electric pressure kind of measurements. But if you're working in kind of a situation where differences in pressure were relatively small, if you use kind of a standard vertical manometer, sometimes it can be a bit difficult to measure or observe any differences in height. So if you're talking about, a column of liquid mercury, right? So if the differences are only maybe 1 or 2 millimeters, that can be, not impossible, but a little bit inconvenient to kind of squint your eyes to kind of see what that difference is. Okay. So the solution to this was to use a manometer that had an incline instead of just a straight vertical tube. Okay, so the idea was the following. So let's say that we want to measure the pressure at point A right here. And just like before, we have kind of a bend down here. Okay? So this often gives way to a gauge fluid. But instead of the gauge fluid kind of going up into a vertical column, we instead have the gauge fluid going up at an incline. Where this distance is measured. Where there would be a free surface up here. Let me actually remove that just to make things a bit easier to see. Right, and so in an inclined tube manometer, you would measure that kind of inclined distance, and that would be your measure for pricing. Right? Now, keep in mind that even though we've changed the shape of the container, it doesn't change the rules of hydrostatics, and so we're still looking at height differences, but the way that we compute height differences now is a little bit different. Okay, so usually your inclined manometer will be inclined at a constant angle theta. Right, and so oftentimes we'll be interested in this height right here. Right, but that height won't be explicitly given to you in the inclined manometer. But you can compute that height based on the length L and the angle theta. You just use a little bit of trigonometry here. The H2 is going to be equal to L times sine of. And so once you have H2, you can just treat this as just a normal manometry problem. It's just that, you just have to take an extra step to get there just to use the trigonometry. Okay, but like I said, inclined tube manometry, not really a thing anymore. And honestly, it doesn't really add anything really interesting to these problems. It's just some complicated geometry. But I thought I would mention it here just for curiosity. Okay. All right. Any questions on that? All right. So we have about 5 more minutes. So there's not much we can accomplish in 5 minutes, but I do want to at least introduce the next topic because the next topic is going to take a while to talk about. We are really going to get into the meat of it on tomorrow. I'm still used to the regular semester. But I would say the next section is probably what people deem the most difficult of this kind of first big unit of fluids. Okay, so the next section that we're going to go over is what we call hydrostatic forces on planar surfaces. Okay. So up until this point, so basically for the entirety of class today, right, we've talked about this idea that if you descend down into a fluid, right, a fluid that's at rest, there's pressures that are going to develop just based on the height differences. All right. So we spent all of today talking about those pressures. But, those pressures, as we kind of talked about at the beginning of class today, those pressures actually exert real forces on objects that are submerged in the water. All right, so let's look at a very simple case first, right? So let's say that we have a container of fluid here. We have our free surface up top here. Okay. Let's say the height from the top of the fluid down to the bottom is given by h. Okay. All right, so if we wanted to compute, let's say we wanted to compute the pressure at the very bottom of the tank, we could do so very easily, assuming that we know the density of the water, of the liquid. So the pressure at the bottom of the tank is equal to, just based on our equations for hydrostatics, is the product of the density of the fluid times gravity times H. Right? So that's something we've done, maybe a dozen times a day or so. And so that's pretty straightforward. But this pressure here is also going to exert a force. And that force is going to be distributed all along the bottom surface of the tank. All right, so how are we going to compute that force? So the force, the way we compute force from pressure is nothing more than just product of pressure multiplied by area. Okay. So we take the pressure that we just computed is just rho times gravity times h. We take the area, assuming that we know the geometry of this tank, right? And that gives us the force. So remember, that's kind of what we did in our derivation kind of in the first half of the class today. Okay. So in situations like this is pretty straightforward, right? So there's nothing too complicated here, because if you think about it, this horizontal surface is all at the same height. Okay. So if you look at a horizontal surface, right, a horizontal surface is always at the same height, and so it's going to have the same pressure applied directly. Okay. Now, what if we had a vertical surface, or even more complicated, what if we had a slanted surface? Right, so there's a difference in height, and often a non-negligible difference in height from one part of our geometry to the other. Okay. Now we still are interested in computing the force, but we have to account for the fact that the pressure at the top of our geometry might be different than the pressure at the bottom of the geometry. Okay. And that's going to affect our calculations. First of all, it's going to affect the magnitude of force that we have to apply. And most importantly, it's going to alter the location of where that force is applied. Okay. All right, but we'll talk about that some more. Okay, but I at least wanted to kind of preview it just so that we kind of hit the ground running tomorrow. Okay. Any questions on this before we wrap it up for today? Okay, all right, so thank you guys for coming today. If you have any questions on this or the homework, just let me know. But if not, I will see you guys all tomorrow.
Yeah, like 12:30.
No, so those are.
Okay.
Why is the problem one? I would do them. I wouldn't do all of them because it's kind of a lot.
Yeah.
But I would pick and choose, just be strategic, and maybe one more time. Maybe go practice with the surf and stuff.
Yeah.
And do those additional. Yeah.
I tried. Or something like that.
Yeah, I'll give you a study guide next Tuesday. Yeah. No, so just do problem 1 through 5, so the section that says additional problem, those are just extra factors for your own. Yeah.
Okay.
Oh, I'm sorry, yeah, I'll send an email about that, yeah,
Okay.
I should.
And then I have a question, so. Yes, you say, section B was central for the no?
Yes,
This summer?
yes.
So I was wondering, can I still take it outside of different school and then I think here?
With labs, it's a little bit complicated because most campuses do their labs a little bit differently. And so I don't think I've ever seen another campus that has a lab that covers the same experiments that we can, at least not in sufficient kind of coverage. So you can look, right? And if you find one that looks similar, you can always apply for approval. But you have to find one that's sufficiently the same. That's kind of hard to do.
Yeah, because I was trying to complete 5 weeks next year, that was my objective, but then since the class got canceled, now it's gonna push me back another year. Because thermals is in spring and then I have to wait for the 76 in the next fall.
So the 476 labs are offered over summer as well. So you'll probably graduate next summer.
Next summer.
Have you come to the department for advising before? Have you ever met with me or Dr. Weiss?
Yeah, I met with you a few months ago.
Okay.
1 or 2 months ago.
Okay.
Yeah.
Yeah, so you're probably gonna be a summer graduation.
Okay.
That's what I'm saying. Yeah, because you'll probably take 306B in spring 27, and then you'll take the 2 476 labs in summer 27. You can take them together in the same summer. That's fine.
Okay. So I was wondering, can I do 476 and the thermostat at the same time or no?
No, you can't. No. Yeah, but 476A, 476B, you can take them together in the same summer.
Okay.
Yeah.
All right, thank you.
Yeah. What's up?
I was thinking, when you were going about the different pressures and stuff.
Yeah.
I was just thinking, like, does that mean like the whole fluid field, vector field is the like it's just conservative then, or like?
Yeah, you can think of it like that. And so it's basically hydrostatics is very similar to the gravity field because that's essentially what's driving the pressure differences. So yeah, you can definitely think of it like that. And in fact, it doesn't really matter which path that you travel within the fluid, right? The only thing that matters is the height difference.
Okay.
Yeah.
Then like its divergence is also zero then?
Yeah.
And also
Yeah.
But for curl, I was thinking like since there's like when you since there's viscosity, then the curl is not zero then?
The curl would still be zero because remember everything right now is still static. And so viscosity actually doesn't play a role just yet. Viscosity only plays a role once you have fluid motion. And so we'll get into that probably in week 3 or 4.
Thank you.
Yeah, no problem. Yeah, great observation.